Okay, well, good morning. Really, it's a totally different topic. I'm going to talk about topological spin textures, and I'm an experimentalist. I'm also going to talk about these in the context of how they might be useful, how we could build useful devices. And I'm going to talk about two types of topological spin textures. Firstly, I'm going to talk about chiral domain walls, and basically how we can manipulate them using currents, spin currents. And then I want to talk about antiskyrmions, which are more interesting objects, magnetic nano-objects that we just discovered last year. And I'd like to tell you something about those. So I'm actually from the Max Planck. I recently moved to Germany 3 years ago from IBM Research in California. And in the last 3 years, have built up an entirely new institute and department focusing on subjects of spintronics and actually also neuromorphic computing ideas. So the context here is that spintronics, we've heard a little bit about spin currents already during these very beautiful lectures. Spintronics is really about how we can create and manipulate spin currents in materials, and then how we could use them to create interesting applications. And today there's only one major application of spintronics, which is in the form of sensing devices used to read information in magnetic disk drives, as shown in this cartoon. And then coming up will be a new application, potentially the second most important application, which is to develop non-volatile memory technologies using spintronic devices to store information. And this looks like this. A magnetic tunneling junction is basically a simple sandwich of two magnetic layers separated by an insulating layer. And the tunneling current that flows is innately spin polarized because of the spin-dependent density of states in the magnetic electrodes. But in addition, the tunneling junction itself can filter out electrons of one spin orientation if up and down spin electrons have different symmetries in their wave functions. And then the penetration depths of the wave functions through the tunneling barrier can be dependent on the spin. This leads to very, very efficient creation of spin polarized currents of up to about 96% spin polarized currents in this very simple device. Using this device, the resistance of the tunneling junction depends on whether the magnetic electrodes are parallel, as shown in the upper cartoon, when the currents can flow more easily, or whether antiparallel, when effectively the current can be nearly suppressed. And this means we have a device that has two states, a 0 and a 1, which we could use as a memory element. And then you can build these magnetic tunneling junctions into a standard so-called cross-point array, as shown here, where you have a series of wires which are crossed with each other, and at the cross point, one can insert this tunneling junction device. And the reason why it's technologically relevant is that you can tune its resistance by many orders of magnitude without changing the tunneling magnetic resistance. I'm not going to talk about these devices. It turns out that we actually proposed using a tunneling junction as a memory element about 25 years ago, and it's only today that finally it will become mass manufactured by Samsung towards the end of this year and early next year to provide a very high performance, non-volatile, dense memory technology. I want to talk about something else, which is basically today many of the memory and computing technologies are coming to the end of their roadmap as we scale transistors and capacitors to their fundamental physical limits. And we need to do something else. And I proposed this about a decade ago, that we could build an innately three-dimensional memory by using magnetic nanowires, as shown in this cartoon. And in the magnetic nanowire, we would introduce magnetic domain walls. And by passing current into this magnetic nanowire, we can manipulate or shift all those magnetic domain walls around the nanowire. When I proposed this a decade ago, it wasn't possible. It hadn't yet been demonstrated. But over the past 10 years, we first demonstrated that this is possible. One can move a series of domain walls with current pulses. But in the last 3 or 4 years, we've discovered a lot of new physics, which is what I want to talk about, as to how we can actually manipulate these domain walls about 10 times more efficiently than was possible even just 3 or 4 years ago. Concept is then we can build billions of these vertical racetracks to build a racetrack memory that would have about the same capacity, we estimate, as a magnetic disk drive, but which would be completely mechanically free, would be a solid-state device, and would be about 1 million times faster and use 50 times less energy, we estimate. So it looks like a very interesting device, and it's perhaps one of the most important emerging non-volatile or volatile memory technologies on the horizon. So I want to talk about this. So you might say, well, this is more like why Racetrack now? And it turns out, as I mentioned, proposed it a decade ago and actually demonstrated it could work a decade ago. But at that time, the domain walls we were using were too wide and they moved at too low a velocity. And moreover, they would interact with each other via their stray fields. And this precluded using these as an interesting technology. However, in the last 3 or 4 years, we've made some very important discoveries. That means we could, using spin-orbit torques, manipulate these domain walls highly efficient, and we could build racetracks from so-called synthetic antiferromagnets, which have no net magnetization, and therefore we can eliminate the dipole fields, and therefore the domain walls no longer interact with each other. This is what I'd like to discuss during this talk. So first, if we go back a few years, then we first explored this concept in nanowires that are made from very soft magnetic materials. And in these cases, there's no magnetic anisotropy, and so the size of the domain walls is determined by exchange and dipole fields. And this means that depending upon the shape and the width of these nanowires, the domain walls would have different widths and sizes. And these domain walls then that separate magnetic domains in opposite directions, these are shown as in the plane of the racetrack, can be detected using standard magnetic force microscopy. And here you can see some vortex walls. And perhaps you can see most importantly that the nature of the vortex walls, you can see the dipole fields change sign from one wall to the next, from the white to the black regions. These correspond to magnetization pointing in one direction and the opposite direction. And in this case, these vortex walls are stabilized at notches in the wire that you can see in the topography shown by the atomic force microscope. So these soft magnetic materials actually give rise to two types of walls as shown here. These are some micromagnetic simulations of these walls. The top is shown a vortex wall. If the dipole fields are big enough, then the material will form this vortex wall to eliminate the poles at the edges of the wire, which otherwise form in the form of a transverse wall shown underneath. And a transverse wall, you can see the magnetization is rotating here from the rightmost direction, which is red, to the leftmost direction, which is green, and points, in this case, towards one edge of the wall as a transverse wall. And of course, there are two types. You can point to the left, you can point to the right, essentially two chiralities. And the transverse walls then are found in thin magnetic layers. As you increase the thickness, you get more dipole energy, more poles at the surfaces, and then the wall will transform into a vortex wall. So these can be manipulated with currents I'm going to briefly discuss. But most of my talk, I want to focus on walls of a very different flavor. And it's shown in the bottom part of this foil. You can see some perpendicularly magnetized materials. And in these perpendicularly magnetized materials, where the magnetization is pointing perpendicular to the racetrack, you can see the magnetization then rotates from an up domain to a down domain, and it can do it in two different ways, typically in a block wall, where the magnetization rotates in this plane defined by the wall, from an up direction to a down direction. And in this case, you get some perpendicular moments to the wall. And in the other case, in a nail wall, which is more important here, the magnetization rotates from an up direction to a down direction in this plane, which is perpendicular to the wall itself. And you can see that in both these cases, just like these vortex walls or the transverse walls, they can have two flavors. They can be left-handed or right-handed. And it turns out we can stabilize one type of chiral wall using means that I will briefly discuss. In this case, the domain wall width then is independent of the racetrack. It basically depends on the magnitude of the anisotropy, which will favor narrow walls, and the exchange, which will favor wider walls. So this is very simple. And typically, the typical materials here then, we can atomically engineer perpendicularly magnetized materials by forming multilayers from, let's say, cobalt coupled to nickel layers or platinum or palladium, where each of these layers is just 1 or 2 unit cell thick. I'm not going to discuss the physics in too much detail, but basically we can drive then these walls using magnetic field or using spin transfer torques by delivering spin angular momentum from spin polarized currents. And then we end up with, in the first case, let's say the field, we have a magnetic field, then as you know, the magnetization will precess around the magnetic field because of the Lorentz force M cross H. And this will continue to precess indefinitely unless there is some damping, some loss of angular momentum. This is what always happens in magnetic systems. There will be some damping, some loss of angular momentum to the lattice through spin-orbit coupling, typical Gilbert damping. At the same time then, if we apply currents of spin angular momentum, shown here on the two rightmost torques, we can deliver two types of torques. A damping-like torque, which basically means that it will be similar to the Gilbert damping, but would oppose the Gilbert damping depending upon the direction of this torque, this flow of spin angular momentum. And it can also produce a field-like torque. And typically, you have combinations of both damping-like torques and field-like torques. And in all cases, because the magnetization is evolving with time, you in addition get Gilbert damping torques as shown here, which are orthogonal to these torques that we just discussed. So in the case of these field-like torques from the magnetic field or field-like torques from the current, then you can see that the magnetization will process around those sources of torque, or in the case of the damping-like torque, eventually the magnetization will become aligned with the flow of spin angular momentum. And as I said, there will be these dissipative torques related to spin-orbit coupling in this way. Well, let's look briefly then what happens in a cartoon. Here is a soft magnetic material. And what happens when you introduce current from a battery into such a material, then you will produce, of course, a spin polarized current, because the electrons, spin up and spin down electrons, can be scattered differently in a system which is magnetic, where you've broken the symmetry so that spin up and spin down electrons are scattered differently. And in typical metals, this happens in all magnetic metals. The current is carried basically by predominantly by one spin polarization of the electrons. And this leads to typically high resistance in magnetic metals. But more importantly, it leads to the possibility that in a simple continuous magnetic nanowire, we can introduce a current, and the current will be locally spin polarized through spin-dependent scattering. And then this spin polarized current can then deliver angular momentum to the domain wall. And so we can adiabatically transfer the angular momentum of these conduction electrons, which are spin polarized, into this wall. And you basically need enough electrons, enough spin polarization to move the wall. And what does this mean? This means eventually, in the best case, you can move these walls at about 100 meters per second. This would correspond to all the angular momentum in the current being delivered to the domain wall. And this is what actually we demonstrated a few years ago. And why is this interesting? Why not use magnetic fields or something else? And the reason is, if you take a simple homogeneous magnetic wire shown in this way, magnetization is along the wire. The colors here represent the direction of magnetization. And here we have two different types of walls, a head-to-head and a tail-to-tail domain wall, neighboring walls. Now, if we introduced a magnetic field, look at the top one first. If we introduce a magnetic field, you can see the two walls will be driven in opposite direction, because the magnetic field will favor one orientation of magnetization, here the red orientation. However, what's really interesting is that if you pass a current into the same wire, through the mechanism I just briefly discussed, these two domain walls will move in the same direction, because the current is locally spin polarized and basically passes that local spin polarization into the domain walls. This is the concept. Using currents, we can move a series of domain walls in the same direction, and by reversing the current direction, we can move them in the opposite direction. This was a proposal that the NIST made a few years ago, and we were able to demonstrate that this actually works. And in simple, soft magnetic metals, you can shift the domain walls in this way at speeds of up to about 100 meters per second. And so this then enables one to consider building a racetrack memory. All one has to do now is to integrate into the racetrack devices for injecting domain walls and for reading the domain walls. So the simplest way to read them is using this magnetic tunneling junction, not as a memory element, but as a sensing magnetic element. And the simplest way to write them is to pass currents in neighboring wires to generate local magnetic fields, but that doesn't scale to the dimensions that are technologically irrelevant. Racetrack also has a very interesting point, which I'm not going to discuss, but actually it's the deterministic switching or motion of the domain walls. It doesn't require temperature fluctuations. Whereas if you want to switch a tunneling junction by passing a current through the tunneling junction, if you pass it low enough currents, nothing happens, and you could read the device. But if you pass a big enough current, again, you can deliver angular momentum and cause switching of the magnetic moment. And if you estimate how much current you need, maybe you're not so interested, but it would take about 10 microamps for 3 nanoseconds to switch an element of the size of about 10 by 10 by 1 nanometers cubed. And that's roughly speaking what one would need to devise if one would want to build a competitive memory using this tunneling junction concept. So you might say 10 microamps doesn't sound like a lot, but it turns out currently not possible to do that with a so-called transistor, which is the same size or the same width as these elements. So one needs to further improve these devices to build the densest possible magnetic random access memory. Now, with Racetrack, it's easier. We can manipulate the domain walls with much less current. I'm going to come back to that later. So let's just give you an example. In the laboratory then, we would just use conventional lithographic means to build horizontal racetracks. And these yellow lines are electron beam lithographically defined contacts. So we basically pass a current along this metal electrode, as you can see here, to inject a magnetic field locally, which will create a domain wall. And it turns out on the right-hand side, you can see how the resistance of this racetrack changes. As we introduce a domain wall, it turns out, typically, it will lower the resistance of the wire, shown here. And now we can move that domain wall by passing a current pulse through or along the wire itself, so we can shift it. And then we can inject another domain wall. The resistance will drop. Again, we can shift it by passing a pulse of current along the wire, and so on and so forth. And we can introduce in this way 4 domain walls. And then as we further shift these walls, we essentially, one wall leaves and we introduce another one. And this, you can see, we can perfectly do this indefinitely, so it's a very highly reliable process. And this effectively is a racetrack with 4 domain walls. So this is a proof of principle of data shifting, which we demonstrated several years ago. Well, this just shows the same thing again. It's a very neat effect. And the problem here, though, is these soft magnetic materials, which typically have these vortex walls. The domain walls are too wide to be useful, limits the density. Nevertheless, we published this in Science 10 years ago as the first demonstration of the notion of creating and shifting a series of domain walls in this way. And so this, if you like, is the first domain wall nanowire shift register in this proof of principle. And I think it's very interesting. If you like, then this is just the first edition of this racetrack memory. The last few years, much more interesting physics that I'd like to discuss in the remaining part of this talk. We're actually using a collaboration. As I said, I was at IBM at the time, collaboration with, I was in California with colleagues in New York at IBM Research Center in Yorktown Heights, and in a collaboration with a research institute in Taiwan. Then we built a completely, fully integrated racetrack memory with an array of 32 racetracks you can see on the right-hand side with integrated tunneling junctions for reading these elements, and we proved then we could build such a device. But too big and not technologically relevant. Now, it turns out that in the last 3 or 4 years, we've actually shown that there's more interesting racetrack memory concepts, more interesting physics. Now, I'd like to briefly discuss this in this way. And just to remind you then, if we could build a vertical racetrack, which is very tough, it would be innately 3-dimensional. I mentioned these vortex and transverse walls, and these vortex and transverse walls have actually, they're chiral. I'm not going to discuss this, but in an array of magnetic wires shown in the bottom, we can show that depending upon their chirality, they will move to the left or to the right through this network. And it's interesting that the topological charges on these domain walls will determine how they can be moved through these nanowire networks. I'm not going to discuss that, but it could be used for memory applications or many possibilities. I want to switch now to this concept of perpendicularly magnetized multilayers, which you could form from, as I mentioned, in particular, cobalt and nickel. And I mentioned already that they have these nail and block walls. So it turns out, I want to discuss this. It's a little bit technical, but nevertheless, I think it's interesting. So you basically have a racetrack which consists of these wires. The green is cobalt. These are like 1 to 3 angstroms thick, separated by nickel, which is about 7 angstroms thick, so just a few units are thick. And what happens is the physics of manipulating these walls is completely determined by layers on either side, above the capping layer, and these underlayers beneath this nanometer thick racetrack material. And this has a lot of interesting physics I'd like to discuss. So just what does it look like then if we have a perpendicularly magnetized racetrack formed not from just a single sandwich of cobalt, nickel, cobalt, but formed from many cobalt, nickel, cobalt layers as shown here, and the capping layer and the underlayer are identical, then these domain walls, this is the domain wall velocity, and this is the current density. There's some critical threshold below which the domain walls will not move because of pinning of the domain walls in these wires. But after they move, you can see they're moving here at about 50 meters per second for these current densities of about 10 to the 8 amps per square centimeter. This is the sort of current density one needs to manipulate these domain walls. And it seems you might think it's quite high, but it's actually not too high. It's actually useful. It is potentially useful. But we can't go much higher than this, otherwise the racetracks will become too hot. So this limits how much current we can put through these racetracks. Most importantly here, these domain walls will move in the direction of the flow of the angular momentum. They're moving along the electron flow at these typical velocities, 50 to 100 meters per second. So it turns out one can do something dramatically different by making the racetrack much thinner. So now we just have a single sandwich of cobalt, nickel cobalt, about 1 nanometer thick. And underneath this sandwich, we place a layer of platinum. It could be something else with strong spin-orbit coupling. Now it turns out this blue curve is what I just showed you. And now you look at the red dots, you can see the domain walls now will move at below a smaller threshold current density, but you can see they're moving much faster at the same current density, several times faster. Moreover, they're moving in the opposite direction from the direction determined by the spin polarized current developed within the cobalt, nickel cobalt layer themselves. So this was a puzzle, and this was first observed not in this system, but first observed by Miron and his collaborators in this very simple system, 6 angstroms of cobalt grown on platinum and above an aluminum oxide layer. And Miron proposed that the motion of these domain walls, which are, again, very similar to this red curve, they're moving at about 300 meters per second, and he proposed that the mechanism derived from a Rashba effect at the interface between cobalt and the aluminum oxide. This leads to an effective magnetic field that can drive the domain walls. So we don't believe that is the correct mechanism, but it was certainly a very beautiful experiment that he first demonstrated this very high speed in the direction of the current flow. But what is the mechanism then? And I want to show you the mechanism a little bit complicated and involves essentially 4 distinct spin-orbit coupling derived phenomena that can manipulate these domain walls very, very effectively. I want to briefly discuss these. You might ask, how do we measure the velocity of the domain walls? And we do that using a simple Kerr microscope. This is the sample we're looking at. It's a wire that is typically 2 microns wide, and we have some electron pads to inject the domain walls. And then here is a sequence of images of a single domain wall, which is being manipulated along this racetrack by introducing a nanosecond long current pulse, typically in the range of 1 to 100 nanoseconds. And then we take an image using a Kerr microscope, which means we simply use a linearly polarized beam of light, and we detect the rotation of this polarization as it's reflected from the surface of these domains. And an up domain will rotate it in one direction, a down domain in the opposite direction. This is the differential image. It's not so easy to do this. And you can see then the domain wall is moving along the wire very systematically. And we can see that then as you like a little movie. These are a series of snapshots of the domain wall along the wire after we have injected individual current pulses. And if we reverse these current pulses, the same domain wall will move backwards. And so we can determine the speed and all aspects of its propagation. So the most important point here is that whether we have up-down or down-up domain walls, then they all move at the same velocity. And this is shown here. These red curves superimposed on top of each other correspond to up-down and down-up domain walls. And you can see the motion is identical. So this means all these domain walls can be moved in lockstep along these wires. If we reverse the current direction, they move in the opposite direction at these high speeds. I want to just show you some experimental data. It's a little bit technical, but it's sort of interesting, I think, because we're really atomically engineering these structures to enable us to see the underlying physics. So I mentioned the data I just showed you. We had a single cobalt-nickel cobalt layer, total thickness of 1 nanometer on platinum. Now we can increase the number of these cobalt-nickel bilayers to 2, to 3, to 4. And what you see is systematically the domain velocity decreases quite rapidly. And so we know then that the effect that is driving these domain walls is derived from the interface with the capping and underlayers. Here it's a thin layer of platinum. And interestingly, we find that, as I mentioned, very sensitive to tiny details of the structure. Here is a single nickel cobalt racetrack on platinum, shown in orange. And now we introduce a thickness of platinum on the top. And so originally the domain walls were moving at about 200 meters per second, but we just add 5 angstroms of platinum on the top, and the speed is halved. And you add 10 angstroms, and it's quartered, and at 30 angstroms, the domain walls will actually be moving in the opposite direction. So it turns out that these upper and lower layers are doing something to manipulate the domain walls, but they're doing it in opposite directions. And so these capping and layers and underlayers can compensate each other. And it turns out if they're equal, then the domain walls will move in the opposite direction, and determined simply by the volume spin transfer torques within the cobalt-nickel cobalt layer. This is what happens. We can change the velocity then from 150 meters per second to negative velocities simply by manipulating the upper interface in this way. So it's a very, very sensitive effect in which we can atomically engineer these motions. And it turns out that we could also not just use platinum, but we can use other heavy metal layers like palladium and iridium. And each of these layers give rise to a very, very strong induced magnetic moment. So the platinum, palladium, and iridium in proximity to this cobalt layer become themselves significantly magnetic. The platinum has moments of maybe a Bohr magneton or so. So it's very, very significant compared to cobalt. However, if we take gold, which is also a heavy metal, then it turns out that this has no induced moment. And you can see here, with gold, the the domain walls continue to be driven by current in the direction of the electron flow. So now they're moving at minus 85 meters per second, but platinum, they move plus 250 meters per second. So it's very sensitive to these individual metal underlayers in this way. And this is just to demonstrate then these concepts. Platinum, iridium, palladium drives the domain walls in the direction of current, but this gold drives it in the opposite direction. And it's amazing that in some sense we can tune these interfaces. For example, we can take this structure with a platinum layer and then introduce a tiny layer of gold between platinum and this first cobalt layer. And just 2 angstroms of gold is sufficient to reduce the net magnetic moment of the whole system by 1/3, which is the magnetism induced in the platinum layer. And it's also sufficient to completely reduce the velocity from 150 meters per second to 0. So you just see 2 angstroms of gold completely breaks this interfacial effect with the underlying platinum. It's extraordinarily sensitive to tiny details. And so if you like, what we have here then is these domain walls are moving at about up to 300 meters per second in this way, and here's 20 domain walls moving at this relatively high speed in the direction of current flow, and with an efficiency several times higher than in these soft materials. Moreover, the domain walls now are just a few nanometers wide, and the racetracks themselves are just a nanometer thick. So one remaining issue here is that these domain walls will produce strong dipole fields. And these dipole fields cause interaction between neighboring domains. So basically, that limits how closely you can put them together. And so to avoid this, we use this concept where we make an artificial anti-ferromagnetic racetrack. So essentially, if you look here, we take this cobalt-nickel-cobalt racetrack, it's actually on platinum, and we separate it by a few angstroms of ruthenium from a second racetrack, which has a similar structure. And if this ruthenium thickness is roughly 8 angstroms in thickness, the two magnetic layers on either side are coupled antiferromagnetically. But if we make this ruthenium thickness a little bit thinner or a little bit thicker, then these racetracks are ferromagnetically coupled. And this is because of a very long-range spin density wave in the ruthenium layer, which is induced by the magnetic electrodes on either side. It leads to this oscillatory interlayer coupling. But if we properly tune the magnetic racetracks and the thickness of this ruthenium layer, we can build a structure with no net magnetization. And then it's quite a surprise. We then discovered that the domain walls move even faster. And you can see this here as we vary this ruthenium spacer layer. We go from low velocity when the coupling is ferromagnetic to high velocity when it's anti-ferromagnetic and so on. And we can correlate the velocity with the interaction through this ruthenium. And so technologically fantastic, this structure with no net magnetization actually enables the domain walls to move 5 times faster for the same current density than in the individual racetracks. And this is shown here. So we can tune the moment in the upper and lower racetracks simply by varying these cobalt and nickel thicknesses slightly. And then if it's ferromagnetic, you get this velocity, 200 meters per second. But as we reduce or compensate completely the magnetizations, then the velocity increases by a factor of 5 to of the order of 1.5 to 5 kilometers per second. So it turns out this is fantastic, this fantastic structure. There's no magnetization. The domain walls have disappeared, and they now go 5 times faster. So I'll come back to that in a moment. It's a completely new interaction. So if you like, we've gone from what was this 300 meters per second velocity in a single racetrack on platinum or other heavy spin-orbit coupling materials. And now we can go in this synthetic antiferromagnetic racetrack. It's more difficult to see the domain walls using Kerr microscopy because there's no net magnetization. And yet they go at this super high velocities. This is quite a surprise. So I want to briefly discuss then how this works. And so I already mentioned we get perpendicular anisotropy simply by breaking the symmetry and introducing interfaces. But there's another very interesting phenomenon which is derived from the interface with platinum. Not only do we get this proximity-induced moment, which is enormous, but it leads to a very interesting exchange. It leads to a Dzerzhinsky-Maria exchange interaction, which causes these magnetic moments to no longer want to be ferromagnetically coupled, but they want to be coupled in a chiral sense so that they are perpendicular to each other, defined by a vector that is defined by this interface with the platinum. And so this is a very well-known phenomenon in many systems with broken symmetry. You can have this type of interaction, for example, in manganese-based spin glass systems where it was first proposed. There's a very simple idea. If you have two magnetic moments separated by some spacing, you can define a vector, and in this way, typically when you have strong spin-orbit coupling, either in these thin film structures or even in bulk materials, this leads to a vector exchange interaction defined as shown here. So it means that the moments want to be perpendicular to each other, but in a chiral sense. This is the most important concept. And so this means in these racetracks, it looks like within the domain walls that you have some effective magnetic field, an exchange field. And this exchange field changes direction from one domain wall to the next domain wall, so that the domain walls will be nail-like because this exchange field is along the racetrack perpendicular to the domain walls. But it means that along this racetrack, each domain wall has the same chirality. So if you like, as you go along this racetrack, the magnetization will be going from an up to a down direction in a chiral helical fashion. Later on, I want to show you how in bulk materials, the same interaction can lead to helical phases, and it can also lead to skyrmionic and anti-skyrmionic phases. So this is this is where we are now. We have chiral domain walls, and now we want to move them. And what is moving them is spin currents derived from the same platinum layer, where we've converted charge to spin using the spin Hall effect. And so this has already been discussed extensively in several lectures, including Claudia's lecture. And just to remind you then, if we take a system, typically with strong spin-orbit coupling, then in conventional metals, you pass a current shown here as yellow, and you derive a spin current which flows perpendicular to the surfaces of this wire, where the polarization of the spin current is along the circumference of this wire. So on the top face, in this particular example, the spins of the accumulated electrons are pointing to the right. But on the bottom interface, they will point to the left. And this essentially is why these interfaces with the cobalt-nickel-cobalt racetrack give rise to opposite effects. Of course, some materials show positive spin Hall angles and some show negative spin Hall angles. But what's surprising is that in the last 3 or 4 years, it's been demonstrated that even in simple metals, spin Hall angles can be extremely large, of the order of 10 to 30%. This is the ratio of the spin current to the charge current. And this was a big surprise and much bigger than expected. So now in this cartoon, you can generate these spin currents, cause them to diffuse into neighboring magnetic layers. And these themselves then can provide torques on these magnetic nano objects or on domain walls. So I think I'm going to run out of time, so I'm not going to discuss how we measure the spin Hall angle, but we can do that using resonance techniques. You simply pass an RF current through this sandwich of a metal and a neighboring magnetic layer. The RF current will both generate an RF spin current through the spin Hall effect, diffusing into the neighboring magnetic layer, providing a torque, and at the same time will provide an amperium field that also generates a torque, but they're in 90 degrees to one another. And we can then look at the resonance properties, resonance excitation of the system, and analyze the resonance excitation for these two torques, and so thereby obtain the spin Hall angle. An important point is that these interfaces have different transparencies for spin current, and even for simple metals like permalloy, the transparency to platinum is much less than for cobalt. It's about 2 times less. So the spin current you generate will be much less effective in manipulating magnetic moments for permalloy than for cobalt. And just as an interesting point that we've heard already in some talks, particularly Claudia's talk about non-collinear magnetic structures, and one of the simplest is in a cubic system, iridium manganese 3. And the manganese atoms on the 111 planes, because they want to be anti-ferromagnetically coupled, but their moments lie in these planes, you end up with a triangular magnetic structure which is itself chiral. And this structure itself gives rise to large Berry fields that we've heard about, and these Berry fields give rise to significant anomalous Hall effects as well as significant spin Hall effects. So and I'm going to skip this, but we can manipulate the population of these domains. You can see the structure. You have 16 anti-ferromagnetic domains along the different 111 planes, and it's a chiral, so there are 2 different chiralities. But we can actually manipulate the population of these domains by exchange coupling to a magnetic layer, and then we find we get a very large spin Hall contribution, larger even than in platinum, and it's about a 40% spin Hall angle. Very, very large. And this has been substantiated by some calculations by Binghai Yang, who showed that this iridium manganese 3 should give rise to large anomalous Hall effects and spin Hall effects, but because of the different symmetries, the chirality does not affect the chirality of the magnetic structure, gives rise to the same spin Hall conductivity independent of the chirality of the domains. The anomalous Hall effect, they have opposite signs, and so it's difficult to measure. And there are some systems, hexagonal manganese 3 germanium, for example, which also has this has a Kagome lattice, chiral structure, but it has a small in-plane magnetic moment that can set the chirality of this structure, and this enabled us to measure very large anomalous Hall conductivities in the system. Now, we haven't yet measured the spin Hall conductivity. So I think you think I should stop maybe? So maybe it's a good point to stop that the spin Hall effect, which describes the conversion of charge to spin, has evolved enormously in just the last 3 or 4 years. And so simple metals that a few years ago were believed to show very little spin Hall conductivities now you can see very large spin Hall angles, 20% in platinum, 30% has been measured in particular forms of tantalum and tungsten by the Cornell group. We've measured minus 50% spin Hall angle, which is the largest yet observed in a conventional metal in tungsten oxide. And there's been some very speculative and interesting experiments that have suggested even larger spin Hall angles in some of these topological insulators like bismuth selenide of 1 to 2, or Kang Wang has even at UCLA proposed a factor of 100 or so. Should I stop there?
No, perfect.
Okay.
Okay, let's thank Stuart again. Are there questions? Yes.
I think our results are very interesting, but I'm wondering how you fabricate these devices. Do you really make the rods with E-beam as well, or do you first prepare the rods and then do the contacts with E-beam with them?
So it turns out that so these materials, even though they're based on layers that are just a few angstrom thick, we make these by conventional sputtering techniques, and we pattern the racetracks I showed you using just conventional optical and electron beam lithography. This is what was necessary. So it turns out that maybe you may be thinking that the line edge roughness will play a role in terms of binning the domain walls. It turns out that's true for conventional spin transfer torques. But these types of torques that I will just get to in the next foil or two actually can overcome very, very significant pinning potentials compared to conventional torques because they have very large field-like contributions to them. And so it turns out that we seem to be very insensitive to things like edge roughness or defects, which is quite a surprise.
And do you have like one sputtering device which can sputter all these different metals?
Turns out we actually in Halle we're building a new sputtering system, which we call Mango. I could show you some videos, but it turns out it has about 45 different source materials. Combining, it's essentially designed so we could explore materials more quickly. It has a very unique design. It has a linear vacuum chamber, which is about 3 meters long. It has 4 subchambers, which each one with either 3 magnetrons or 5 effusion sources. We can interchange these whilst maintaining ultra-high vacuum in this upper chamber, because these individual subchambers are separated by differentially pumped gate valves. This system also has ion beam magnetrons sputtering from 3 distinct sources, 3 targets.
Will all be sputtering in all the courses?
It will be sputtering there, but these subchambers, we can replace them with a subchamber that contains 5 effusion sources. So you can innately combine molecular beam epitaxy with magnetron sputtering, with RF sputtering, with ion beam sputtering. It also has an ability to cool the substrates because you want to go to high temperatures typically very quickly for smoothing them, things like this.
More questions?
So.
Okay, then I have a naive one.
Okay.
Basically, the racetrack memory is based on sweeping domain walls back and forth. And how does it affect the way you would read like a given sector of memory in a hard drive, let's say? Then you would, how many domains would you have to sweep? Do you need to think about new designs of memory? And in the end, how can you estimate how fast such memories would be?
So it's a very good question. So you're totally right. It is a shift memory. And 40 years ago, in the very, very beginnings of computing age, there were shift memory technologies. So that means you actually do need to completely change the circuits and your approach to using this type of memory. Because we're thinking that maybe we want 100 domain walls in one racetrack. So to read one of these domain walls, you'd have to move 100 to the reading element. However, it turns out it has a very interesting point that in the same technology, you could choose to one racetrack, you might have said, oh, let's only store 1 domain wall. So then the latency to read it would be very tiny. And then in another racetrack, you store 100 domain walls. So the latency would be more, but you get a much greater density. So you can do this dynamically. You can dynamically trade off latency, performance, versus density. And there's no other memory technology can do that. So it turns out in Dresden, there's a Center for Frontiers of Electronic Devices that now we're part of. And a lot of computer circuit engineers, scientists, who are really thinking deeply about what this might mean for computing systems and technologies. And actually, turns out there's many, many papers about exactly this question. It's a very, very interesting one.
Okay.